Good afternoon. My name is Ricardo, and today I'm going to present the final project. Basically, it is a new optimization on Cortex-A72. The framework that I was working on is the NTRU, the 2048677. Just for you to know, there is a prior art that already exists for this implementation, and this one is already on using Neon, but there is plenty of room for optimization. Basically, there are some operations, specifically Toom-3, Toom-4 and Karatsuba, that can be combined, and there is a lot of code optimization in sense of removing redundant functions and cleaning some variables, and also removing redundancy. That all this can be done in the implementation, in the prior art implementation. So there is plenty of room to optimize the solution, right? So first of all, I would like to say that I tested the code in two different test beds. The difference is not that big, but it's a substantial difference in the sense of memory usage. Um, as part of the course material, we received a 2 GB version Raspberry Pi 4. But by myself, I also already had a 1 GB version, and this is like a limited edition. So I tested on both of them, but still like Raspberry Pi 4, which they both have the same CPU, the A72, right? And I tested in two different operating systems. For the 2 GB Raspberry Pi 4 version, I used the Ubuntu 22.04, and for the 1 GB edition is basically the Ubuntu 2004, right? And both of them are on the server editions. For GCC, I use the GCC 10.3, and also the language that actually was used for the implementations was C and Neo Intrinsics. There are special notes that actually must be mentioned prior to starting the explanation. First of all, as I mentioned, there is already a prior art, which is here in the reference. Um, but the prior art, it can be enhanced. That prior art attacks not only the version of Intrude that I'm using, but also like a different versions. And also, they reuse a lot of the code. There is some redundancy, and actually by basically staying in one implementation and removing that redundancy, you can speed up the process a lot. Also, the even though the prior art was performed using Neon intrinsics, there's still plenty of room for the parallelization process, right? So another thing is that actually parallel implementation not necessarily is faster. You need to keep in mind the architecture of the CPU that you're using. In this case, because Cortex A72 uses 4 CPUs, um, keeping everything in multiples of 4 is way more convenient, because it will help you to basically perform the optimization better. Only problem is that sometimes it's not that human readable, but if you keep track of like the variables and you keep track of what you're doing, then there shouldn't be any problem, right? Third one is that actually, like, in order for us to keep using multiples of 4, is that actually we use arrays and pointers of the traditional unsigned int 16 and unsigned int 64 and 32 variables. But there was like the neo intrinsics, unsigned int 64 time, like two of them, and also the 4 and the 18. Like basically these ones allow us to call the neon functions that can run in parallel several operations in the CPU, right? Um, Another thing that actually this is not mentioned in the presentation, but I would like to mention is that for the developing, we like I use the Visual Studio and connected by SSH to the Raspberry Pi. Why I use Visual Studio and not develop like as a normal like a Visual Code or like a normal notepad is because the Visual Studio provides a lot of tools, not only like because it's already a really mature developable environment, but also like it allows you to have like several different functions. For example, like search for occurrences, and also like when I will show you like a real demo, retail demo, we will see the assembly line by line, and also like the memory access and like the variables values, right? So basically, like in this case, we use like a Visual Studio, and we can connect by SSH to a local network that I already created to the Raspberry Pi. Okay, so basically in this case, we connect to this one, to the 05, and here is this one. So if I check the IP, it basically is 05. Okay, so okay. Okay, for the prior art, as I mentioned, the prior art is really good, but there's room for the optimization, right? I will say that actually this is because like the prior art reuses some of the code in several different implementations, so you cannot do like a really optimized version. You know, for example, Intro, like in each one of them, because it's like it's better to reuse some of the code, right? Because it's like in the prior art they attack different Intro versions. Meanwhile, in our case, I mean, like for the class, I'm just basically like working on one version, right? Um, for the prior art and my solution, the memory usage is the same, but how the memory is accessed is different. So like I'm not going to basically like transform data into a different value. I'm just basically like modifying how the memory is accessed. So that way we can reach the thresholds asked for the final project, and it's easier to keep track of what's happening, right? Again, the prior art has redundancy, and because some of the functions are reused in different places, right? And what we aim to do in this case is to basically like to first of all modify how the memory is accessed, and second is to combine some of the functions. In this case, is like the interpolation recomposition stages of Toom-3, Toom-4, and Karatsuba. Steps can be recombined into like really can be merged into a couple of functions, so that way the implementation is faster. Okay, so this is how in the prior art how the memory is accessed. So as you can see, there is like a plenty of multiples of 4 in this case, right? And we're going to keep basically the same approach. Only thing is that the accessing time and accessing like the order will be slightly different. Okay. So let's see how, like on the paper, they refer to Toom-4 as TC4. Right? So we're going to see how the combination of Toom-4 and Karatsuba is done in the prior art, and how we are going to do it in the in our solution. Okay? So basically, like the original approach, it has a really clear path. So what it does is basically like for the Toom-4 implementation, it performs like a split and evaluation, right? This is part of the algorithm, right? And this is like they perform like this amount of operations, right? Now, Karatsuba also perform the same split and evaluation, right? But like we are right now, I'm going to show you how the memory is accessed, which is not that optimal, right? So basically, because of the non-optimal approach, there is room for a new recombination, right? So we can recombine some of the Toom-3, Toom-4, and Karatsuba interpolation and recomposition sections, and basically we can just make some functions. Just for you to recall, here is the Toom-3, Toom-4, and basically like the Karatsuba part, right? So we are going to recombine some of their stages. Okay, so basically this is how the memory is accessed in the prior art. So basically what it does is like they go by 2 by 2 by 2 by 2, right? In the original like 60 times 4 array, right? So basically what it does is basically like the 2 4 is split into this way, and then basically on the evaluation part is going to be accessed like by 7 times, right? Like this is 1 2 3 4 5 6 7, and each time is going to be accessed when like in sections of 2, right? So basically like the access is being done, and then is perform a Karatsuba, right? Like a Karatsuba process here, right? So from that to obtain the result, this must be repeated in every other block, right? So basically we have 7 blocks, so we have to perform all the Karatsuba until this point, and after that we can obtain we obtain the result, which is a polynomial, like 15 polynomials of that size, right? But the problem is that actually the prior art takes too long to finish. So it's basically because it has to wait until the end result to obtain like the final polynomials, and also there you have to wait by like several steps, and also there is no need for us to wait like on every two steps, right? We can just basically try to access in a different way. So that's the reason why we're going to use a different, in this case, a clever parallelization, right? So we are not going to wait for everything to be finished in order to get the results, right? So what we're going to do in the optimization is basically several things, right? First of all, this is like the summary of the optimization. First of all, like the matrix transpose was like the redundancy was removed. So actually, we got around 1,500 cycles less after we removed the redundancy. Also, there was like a Toom-4 and two Karatsubas that actually were combined, like the split and validation sections were combined. So basically, it is around 2,200 cycles less. Then like a Toom-3, Toom-4, and Karatsuba, basically like this is, I would say, the most important part in sense of the cycle reduction. It's basically like because we combine the interpolation and reduction sections, right? Which is like almost 6,000, 5,800 cycles, right? Then there was like in the prior art there was like some garbage cleaning process. Like for example, there was like some steps that actually you need to um, add zeros and basically clean like the arrays. So that takes some time. So if you remove that part but still like keep track of what you're doing, then you can save another extra 1,000 cycles. And then for the final one is the code optimization, right? So there's some in the prior art there were a lot of classes that actually the compiler must try to merge into the executable, right? And also like in the case we can just basically merge like those classes into one class, and also like remove some of their redundant functions. Like you will see that, for example, and here like the class is quite big. So, and also like these are part of the functions that are the, well, in this case defines as some of the functions that actually are present in the prior art, but they are not all of them. So you see that there is just like a couple of them. So here you see it, right? So the way how you can remove it is quite easy. Just basically check where they are being called instead of the functions, and basically like just remove them, right? And here is basically the part of the transpose matrix transpose that actually we fix. Okay, so basically these are like I would say the main steps that actually were performed to optimize the code. So in the optimization technique that actually use is to access the memory in a different way. So for example, instead of having like two like as in the previous time, we're going to access like in a different way. So we're going to access like first of all like the odd positions, right? And then like from these ones we can just get like part of the Karatsuba, right? And then like the even positions. So then like the approach is reduced a lot, right? This is basically on the Toom-4 and the Karatsuba, the evaluation and the split sections, which I think it's a quite substantial reduction in terms of performance, right? And then you can just obtain the final polynomials like at the end, right? So about the interpolation and evaluation combination, right? That actually was performed. Um, like this is basically like after you perform the evaluation split, right? The interpolation evaluation. Basically, it's there is already in the original code there was a combination function, but it didn't seem to make that much sense in sense of like just for the NTRU version, like the 20486677, right? So basically, like the new combination function, it was inspired on the prior work one, right? The prior work performs 5 interpolations and 1 recomposition, but actually they perform them in some sort of a linear way, so you have to wait for everything to be finished. But in our case, like for the new solution, what I did is basically you can reduce like the almost half of of the execution just by the clever parallelization, right? So you can see is basically like is this function. These two functions that actually are this one are this one Toom and Karatsuba combined, right? So here is basically like a new combination function, right? So basically from the results, after the optimization process, basically like almost half of the cycles were reduced, right? So basically we obtain a speed of around 45,000 cycles. And basically like there are some instructions that they were easy to parallelize, and there were other ones that actually they were not. So it's basically like the best ones are basically the ones that actually include several parallel and non-dependent accesses to memory, like for example like when you split the polynomials by sections. So basically when you start multiplying them, right? And there's still room to improve. What I saw is that actually we can add an extra Karatsuba cycle there, but because of time purposes, was not able to add it to the implementation. I think actually if I added it, then the cycle could be reduced way more. Okay, so this is like a screenshot, but I will also give you like a live demo. So basically, like here is like the renal from the GitHub, like the renal code. So you can see that actually the test is passed, and also the like when you run it is basically around like 90,000 cycles, right? And after you run it, then like this is the optimized version. Then like you get well, in this case it's 44,000, but it's around the 45,000s, right? So for example, for the live demo, right? So here is the original code. So this is like the entry part that actually like the TA told us to not modify. Right now, I guess I can make this one slightly bigger, right? So basically, here is the access function, right? So at least for to implement to compile and deploy from Visual Studio, you just basically have to connect by SSH. This is right now connecting by SSH to the Raspberry Pi. So basically here is the clean and then rebuild, right? Oh, there's one thing. Right now it's going to rebuild without the, oh no, right now it's running with the -03. The thing is that if you compile with the -03 flag, then when you debug, the debug point starts jumping a little bit erratically. So for example, you want to debug this one, then it's not going to stay there. It's going to basically move from place to place, or it just stops in a different place. So if you want to debug, you have to modify this flag and remove this one. So this is in here. So you just remove, I'm going to show you right now, because it's like right now, for example, here, if I try to debug this part here, for example, if I try to debug these ones, is not going to stay here, right? So right now it's already deployed to the Raspberry Pi, which is here, right? So if I can just basically make, all right? So just it basically is the same. Here and here is the same, but it's just going to show you, right? Right now it's running with the 03 flag, all right? So just so right now that it's testing it is passed, and for the speed, right now because it's running the 03 is going to have a good speed, right? So, huh? Okay, sorry, sorry, I wasn't sure. I'm running the GitHub one. This is the final project one. Okay, sorry. So let's make, okay, to make. So here is like a running with the -03, right? So if I do the test speed. Okay, so here's we're getting in 45,000, right? So, but the problem is that, for example, if I want to debug, right, then like it's going to, or at least for the with the -03 is going to jump a little bit radically. Also, right now there will be a new window appearing on the right side, and it will show the assembly and the array values in real time. Okay, so here's this thing, right? So let me just move it here. Okay, so for example, here, as you can see, the debug pointer is basically pointing. I already skipped the debug points that actually I tried to implement. It is because it's running the 03 version, right? So, but here you can still see the values, right? And also you can see the I think actually the point is completely there. You go. You can see the the values here, but right now because it's optimized, it hasn't reached a point, right? So it's optimized, then you're going to be jumping from part to part, right? But now if we debug the non-optimized version, right, which is removing the let me just make it bigger. If we remove this the 03 flag, right, and then clean and build. Okay, so then for example here, I don't know, when I try to debug, right, in this point at this point, then I can just basically run it, and you should stay here, and you can access the function, and you can see like what is happening, right? Again, the assembly window will appear on the right side. There you go, and now you see that actually the debug point, it stays where I created the breakpoint, right? So for example, if I access here and I want to see like what is happening, then you will just basically get in. And for example, for this one, right? Let's suppose that actually we want to just stay here and see what is happening, right? Then when I reach that point, which is this one, here I can see, for example, like the values of the arrays, and also the assembly, like the assembly yeah, here it is 0 right now, the assembly code that actually is going to be executed, and you can also be jumping from line to line and see what is happening. Okay, so okay so basically some conclusions of future work. The prior art has plenty of room for optimization, because it's like as an end result, I was able to reduce half of the execution time, and well, basically like obtain a final like a clock, like a cycle count of around 45,000. And again, in the future, an Karatsuba cycle can be added into the original code, but actually I was not able to do it because of time constraints. And there's another way to improve the matrix transpose function. I think a better approach might be possible, but like again, because of time constraints, I wasn't able to do it as best as possible, right? But I think that actually at this point, like with the 45,000 results, is basically more than enough, right? And just for references, basically, like I think that actually this is the one that actually the TA providers in the slides. So this is the best one, and also like I think it's quite interesting because it's like it has plenty of other implementations. So I think it's quite a challenging to optimize all of them, and it could be a really nice research work just to basically make a extremely optimized version of all these works. Okay, so basically that's it. I will upload the project and also the video to NTU Cool and also for GitHub. So if you have any questions, please just send me an email. Thank you.